This is Chapter 5, Problem 17. Here we have a mass that's on an inclined plane, and the mass is being held up by a rope attached to the wall. Now, whenever we have these inclined plane problems, we have to be very, very careful how we draw the free body diagram. So that's why I'm going to take the time to do this. I've drawn the inclined plane. It has an angle of 30 degrees, and I've replaced the box with just a dot because I'm going to do the free body diagram. First thing we need to do is draw the easiest force, and that would be the force of gravity, and that's going to act straight down. So there's mg. Okay. Now, Dr. Schmidt likes to talk about tilted head world, which is all well and good. I'm totally fine with that. But what we need to do is we need to figure out the force down the incline and the normal force. If you notice, the normal force is going to be at an angle. The normal force, if I draw it, is going to be something like this. There's the normal force. Recall that the normal force has to be perpendicular to the surface of contact. So it isn't just simply mg, because obviously mg is going straight down along the y-axis, and the normal force is at some angle. So what we need to do is we need to draw a new triangle, something that looks like this, tracing down like this. And then I'm also drawing this bottom portion here that is parallel to the hypotenuse of my inclined plane. So now I have two forces here, with mg acting as the hypotenuse of this triangle, and these two lines, these two dotted lines, meet at 90 degrees. So I have a new right triangle. If you go back to do some right triangle trig, and feel free to ask me about this in class, you'll find that the angle at the top of this new triangle is also 30 degrees. This has to do with alternate interior angles and a lot of trigonometry that I've forgotten, but I brushed up on a little bit. Now we have these two forces coming from, these two dotted line forces coming from the hypotenuse of my triangle. This force at the bottom, I call this F down the incline. That's the force that this mass is going to feel down the incline. If you take a second to put your pencil on your physics book and slowly start to incline your physics book, you'll see that the pencil will start to fall down. We can rewrite that force up at the top on our free body diagram and list that as F down. It's acting on the mass on the inclined plane. Now this other force right here, this other dotted line force, is going to be the normal force. That's how we're going to find it. If you think about it, if the normal force was greater than this dotted line force that's acting in the opposite direction of it, then either the mass would go shooting off, and it would kind of be like a launcher effect, or if it was less than, then the mass would start to sink in through the inclined plane. So that means that we can find the normal force. F down is going to be equal to, from our new triangle, mg multiplied by the sine of theta, and the normal force, given our argument just a second ago, that's going to be equal to mg times the cosine of theta. Now quite directly, one of the parts on the problem is asking for the normal force. So that is going to be equal to the mass of the box, which is 8.5 kilograms, multiplied by 9.8, multiplied by the cosine of 30. And I didn't quite fit it. There we go. That's close enough. And so the normal force is going to be equal to 72.14 newtons. So that's our first answer. And now they're also asking for the tension in the cord. Now if I go back to my free body diagram, I notice that there's going to be this tension up here. That tension in the cord is going to counteract the force down the incline. So if I solve for the force down the incline, I am also solving for the tension in the cord. So the tension in the cord is also equal to F down. That's mg times the sine of theta. And so now if you substitute in your values, you're going to get 41.65 newtons. M is 8.5, G is 9.8, and you're looking for the sine of 30. For the last part of the problem, the cord is now cut, and now we need to find the magnitude of the resulting acceleration on the block. Well, now we have a very real net force, and that net force is going to be equal to the force down the incline, F down the incline. We found F down the incline to be equal to 41.65 newtons. 41.65 newtons. We know that force is equal to mass times acceleration from Newton's second law, so 41.65 is equal to the mass times the acceleration, or just 8.5 times a, and we can solve for the acceleration of the block as 4.9 meters per second squared. And now, since the acceleration needs to have a direction, I would say that this is 4.9 meters per second squared down the incline. Down the incline. That just lets me know the direction of our motion.